All right, now I finally get to share with you a method for average treatment effect estimation based on machine learning that's actually good. So, all right, what do I mean by this? Well, the average treatment effect, we've been talking about it for a while. We want to estimate the average treatment effect under unconfoundedness. There's no question here, but of course, the thing I've left more implicit, what do I mean by actually good? And by this, I mean an estimator with kind of parametric type guarantees. We want an estimator tau hat that converges to the average treatment effect at a Rudin scale that satisfies the central limit theorem, and that's going to enable us to build confidence intervals in the usual way. Why is this a notion of good? Well, if in the classical setting of parametric modeling, if you were to run linear regression with a well-specified model, this is essentially what you'd expect. You could get Rudin rate confidence intervals. So if you're using machine learning, then you'd hope that at the end of the day, you get something with comparably good properties as to what you could get out of traditional parametric modeling, but just kind of under more flexibility. So this is what we want. What do we have? We have machine learning, but that's, of course, again, rather nebulous. So now I'll need to be more specific again about what I mean by access to machine learning. And by this, I mean we have access to a predictive black box that's good, that's flexible, but that's not too good. And what I'll assume specifically is that we have a way of estimating these mu hat and e hat, these mu and e functions, the conditional response function and the propensity score, that converges in root mean squared error at a 4th root n rate. Here, remember, n is the sample size. So this might look like something of a strange assumption. Okay. Why this? Well, the first thing to note is kind of how are we writing this assumption down? And we're writing this assumption down in terms of the root mean squared error, RMSE. Why is this natural? Well, remember the claim of machine learning methods is that they're good at, the claim is that machine learning is good at prediction. Under squared error loss, like I mentioned earlier, being good at prediction means having small mean squared error. The optimal predictor under squared error loss would just be kind of using mu wx and efx. The optimal prediction of yn. Y giving w and x is mu wx. All right. So machine learning claims to be good at prediction. That means it must be claimed to be good at RMSE. And also, in fact, if you tune your machine learning method for predictive accuracy, then you're simultaneously tuning it to be as good as possible in terms of RMSE. So the reason I want to be using this assumption is I want to be assuming things of machine learning methods that they actually claim to be good at, as opposed to assuming something else. So this is about the functional form. The second question is why the 4th root n here? This is a more delicate question. If this were kind of a stats PhD class, I would talk for a while about the exponent here and debates about what is the optimal exponent here and trade-offs. But for our purposes, the main things to note is first, this rate of convergence, 4th root of n, it's smaller than 1 over square root of n. That is kind of for big values of n, 1 over 4th root of n is bigger than 1 over square root of n. So this is a less stringent assumption. If you had a parametric model, then traditional parametric methods of estimation could get you 1 over square root of n rates of convergence. And here, what we're assuming is that you have some convergence guarantees that are weaker than 1 over square root of n. That's the important thing. We're not assuming parametric convergence in. And now we need some number here. I made a big deal about why this is kind of a weaker guarantee than assuming 1 over square root n rate convergence. Now we need something here, 1 over 4th root n. I'm just using it as something that's convenient, that'll enable simple formal results. And that's also kind of obviously weaker than what you get in parametric problems. So there's some room for kind of machine learning to be doing a good but not perfect job at prediction. So, all right, this is what we have. And then the question is, how can we use this predictive white box to reach our goal? That is, estimate the average treatment effect. And so the answer ends up being, we've talked about methods based on regression adjustment, where you only estimated the mu functions, and then you try to form an average treatment effect estimator based on those. And that didn't really work. And we've talked about methods based on inverse propensity weighting, where you only estimated the propensity score, the E function, and try to use that for average treatment effect estimation. And again, that wasn't accurate enough. What's going to work is that you need to estimate both models and combine them in a clever way that trades off the errors of each model against each other. And how do you do this? Well, for now, I'll just write down the answer. You want to use the following functional form for the estimator. This estimator is called the augmented inverse propensity weighted estimator, or AIPW. And the short story is that in considerable generality, this is a good estimator of the average treatment effect, even when your mu hats and E hats were obtained from a machine learning method. So I guess in looking at this, your first reaction might be like, that's a cool guarantee, but maybe you feel like I've lost you here. This is a very complicated looking estimator. I feel like, Stefan, I like what you're telling me, but I've never used an estimator in any of my papers that took 2 lines to write down, and maybe you don't feel like changing that. And I understand the sentiment, but I hope I can convince you that the estimator, kind of once you understand what it's doing, it's not quite as bad as the functional form suggests. So what's going on here? Instead of just writing it as a giant blob, let's write it in 2 parts. First, I'm going to kind of cut it up into the orange part, and second, a blue part, which is kind of the rest here. And now, okay, if we write these 2 parts separately, so we have the blue part and the orange part, these are the same from last slide, then we can interpret them as follows. The orange part, this is actually something familiar. This is something we've seen before. An average from I equals 1 up to n of mu hat 1 of xi minus mu hat 0 of xi. This was just the machine learning based regression adjustment we talked about at the beginning of this lecture in part 2. We talked about how under flexible conditions, the mu hats you get out of machine learning are going to be consistent. So this term uppercase D is going to be consistent for the average treatment effect under considerable generality, but the machine learning methods don't converge fast enough, and so D is not going to converge at a square n rate. There's going to be bias, and we can't get confidence intervals. So D is something we had seen before. Then the question is, what is this R term here? This is kind of a correction that we apply to D. And here, if you stare at this and you compare it to the IPW estimator we just saw earlier, this should actually look quite familiar. What was IPW? IPW looked like this. So IPW was the average over n of I equals 1 up to n of wi over e hat times yi, and 1 minus wi over 1 minus e hat times yi. So if you just had the red stuff here, then this term r would look like what you got out of IPW. This was the thing we had before. What happens now is that this term r is applying IPW, but it's not applying them to the original outcomes yi. It's applying them to these residuals here, yi minus mu hat 1 of xi in the case of the treated units, and yi minus mu hat 0 xi in the case of the control units. And This might seem like a strange thing to do, but here's the intuition. Imagine you were kind of listening along in part 2 of this lecture with the regression adjustment, and you kind of liked the regression adjustment, and you felt like this was a pretty good estimator. But then I told you, look, machine learning methods have errors. The regression adjustment leaves these errors on the table. This means there's bias, so we can't use the regression adjustment alone. You feel, okay, maybe this isn't perfect. Maybe the regression adjustment left some signal there, but I'll just try to patch it up afterwards. I'll try to kind of salvage that signal and kind of apply a correction to the basic kind of regression estimator, capital D. So here's what's going on. This kind of yi minus mu hat 1, this is kind of a measure of how much signal, kind of if this mu hat 1 of xi were a perfect prediction of yi, so this was kind of just mean zero noise, irreducible noise, then this kind of R term would be essentially 0. But if it's true that there actually is some signal left over from the first regression stage, then you should expect that there's some signal left here and some signal left in these residuals that kind of is a measure of the bias of this pure kind of orange regression adjustment estimator. And now kind of you might have this wild hope that you can just take these residuals and extract the information that was left over by throwing these residuals into IPW. Kind of, you start with the regression. You have two ways of estimating an average treatment effect, the regression adjustment and IPW. So what you're going to do is first run the regression adjustment and then use IPW to fix up the regression adjustment and kind of soak up any information that was left over. This might seem like a wildly optimistic idea, but turns out it works very nicely. So let's see this play out in an example. Here, it's a simple simulation, not a parametric function. Notice these positive parts here. And we want to estimate the average treatment effect. The average treatment effect in this setting is going to be negative 0.05. First thing you could try, just estimate these mu0, mu1 functions using a random forest. Take the average difference in predictions. This is the regression adjustment estimator. You can do it. It's going to be consistent. Is it going to be particularly good? Well, here, on average, we get an answer of 0.09 when the true treatment effect is negative 0.05. Okay, but not great. So what we're going to want to do is then patch this up and correct it. And so here what we're going to do in the second step is we're going to fit a propensity model, E hat. We're going to apply IPW to the residuals of the random forest. This is going to give us this correction term R, and then we're going to add this correction term R to the original estimator. So here the correction term R is negative 0.1. Our estimator from before was 0.09. And when you add them together, then you get this point estimate of negative 0.01, which again isn't perfect, but it's a lot closer to the true answer than the original regression adjustment. To kind of get an idea of how good is this, I'm here showing a box plot of kind of across 100 replications of the treatment effect estimates you get. So here, this is first the box plot of the regression adjustment estimators. And you see it's really not that good. Kind of the true answer is here, negative. On average, the treatment effect here is positive. And not only that, but kind of in every single realization in the simulation setting, the regression adjustment gives you a treatment effect estimate that's bigger than the truth. So you don't even have any spread of this box plot around the truth. Then here, this is the correction. It's a remarkably stable correction here. It just kind of pushes this box plot down. And then AIPW, what you get? Well, you get the following. It's again, not perfect. We're not nailing this answer. This is again kind of there's some finite sample phenomena here suggesting we're not kind of in a perfect asymptotically unbiased type regime yet, but still on average AIPW is much closer to the correct answer than the kind of regression adjustment and its own. And also you see that now at least the true treatment effect starts to be within the spread of things you could get out of AIPW. And there are some simulation replications where AIPW falls below, kind of is negative, has a negative rather than a positive error. So here the correction helped. All right. An aside I just want to make still, so I hope this helps a little bit in reassuring that this kind of daunting AIPW functional form, it has a simple explanation. It's run a regression adjustment, then take the residuals and stick them into AIPW. Even so, you might feel like this is a lot to implement. And again, something I kind of want to reassure you is that kind of once you know that AIPW is a thing you want, is the thing to do when estimating average treatment effects using machine learning, then kind of hopefully you can find a software-based solution that implements it for you. For example, in the package GRF that Susan and I maintain, you can run this function causal forest. Under the hood, what this is going to do a bunch of stuff. We're going to talk about it more in upcoming weeks, but it's going to give you the mu hat and e hats based on random forests for the things you need. And then if you want to run AIPW, you can just call a function average treatment effect on the causal forest object, and we're going to do all of this for you. So anyways, it's a question. In some cases, you may want to implement this on your own, but often when you're running this in practice, you don't need to deal with kind of the massive functional form. All right, that's AIPW. That's what it looks like algorithmically, procedurally, but I've been kind of hyping this up for a while now, saying that it's good. So let's actually talk about the sense in which AIPW does give you a good estimate of the average treatment effect. And the key result here is that AIPW actually satisfies the theorem that we tried to prove about IPW, that is just kind of plain inverse propensity weighting, but didn't go through. And so like did there, I'm going to start by writing down this oracle version of AIPW. So if you remember from a couple slides ago, this thing I'm highlighting in orange, this is exactly the same as the AIPW estimator, except every time when there's a mu or an e, I'm putting the true value of mu and e in here, not the estimated mu hat or e hat that you got out of the machine learning method. And the strategy here is going to be to show that under reasonable assumptions about the machine learning methods, that the feasible AIPW estimator that uses these kind of estimated mu hats and e hats is going to be equivalent to first order, is going to behave just like this oracle AIPW estimator that uses the true values of mu and e. In the case of IPW, we tried to prove this kind of result, but it turned out that kind of, at least using our proof strategy, the discrepancy between the feasible tau hat and the oracle one was much larger than the kind of target error scale, whereas here the opposite is going to be true. And the theorem is essentially the following. This is kind of a very simple version of a result of which there are many alternatives out there in the literature. I'll point you some more references at the end of this lecture. But so let's start by assuming what I assumed earlier, that is that all our estimates we get out of machine learning are not perfectly accurate. They're not converging at a root-n rate, but they're pretty accurate. They converge at a fourth root rate. Then the feasible estimator tau hat and the oracle up there in orange are equivalent at the square root n scale, meaning if you take their difference and you blow it up by square root n, this converges in probability to 0. They're first order equivalent. I'm not going to prove this result here. It's beyond the scope of this class. If you want to see a proof, please send me a note. I'm happy to share a reference. In particular, on the last slide, I'll have some references that kind of prove this kind of result in the case of specific machine learning methods. Also in the Stats 361 class I teach, there are lecture notes that I referred to in the syllabus. And in chapter 3 of those notes, there's a proof of this kind of result. But for now, I just want to kind of emphasize the form of the result and contrast it to what we got with IPW. With IPW, we kind of tried to bound the discrepancy between the oracle and feasible estimators. And what we found is that if the propensity score converges at 1/4 root n in root mean squared error, then the discrepancy between the feasible and oracle estimators, well, you can bound it to order 4th root n. There was no gain there. You were limited by the accuracy of the method you put in. But here something else happens. We have a bunch of regression adjustments, and we're only assuming that they converge at 4th root n. And yet, the error, kind of the effect of kind of plugging these mu hats and e hats with 4th root n scale errors into this estimator results in kind of only alters this estimator to scale that's less than 1/root n. So this somehow violates this garbage in, garbage out principle, where you think if you kind of plug stuff into here with 4th root n scale errors, then you must kind of induce 4th root n scale errors in the final product, but that's not true. You can plug in 4th root n scale errors, but essentially this estimator is very carefully designed in a way that makes it that kind of first order errors in mu hat and e hat cancel out. And that's why kind of you can plug in components with 4th root n scale errors into here. And in the end, you change the final result by less than 1/root n, and you get this kind of result here. What this means is that we can do what we actually wanted to do with IPW. That is, we can just study this object, give a central limit theorem for it that's going to converge at 1/² rate, and then we can use this kind of result to invoke or to argue that actually tau hat AIPW also satisfies any guarantees you proved about tau tilde. And kind of concretely, right, just again, this tau tilde here, if you know this mu e stuff, again, this is a big expression, but this is just an average of IID terms. Averages of IID terms satisfy central limit theorems in considerable generality, as discussed earlier. So what you can check is that this oracle estimator is going to be asymptotically normal with 1/root n deviations around the true average treatment effect tau. You can check that its variance is going to depend on this quantity v star spelled below. And really the point here is that because tau hat AIPW and tau tilde AIPW are equivalent on the root n scale, then kind of once you got this central limit theorem for the oracle estimator, you also get this central limit theorem for the feasible estimator, where we plugged in machine learning-based nuisance parameters. So this is the first result I've given you today, where you don't need to use parametric models. You can just start from kind of machine learning, reasonable assumptions on machine learning, combine predictions from a bunch of different machine learning models, and you land on your feet. You get an estimate for the average treatment effect that has classical Gaussian parametric rate behavior. So you get a central limit theorem. That's very good. It turns out actually that this V star we got here, it's a very good variance parameter. And actually, this is the best central limit theorem you could get for average treatment effect estimation using any method under kind of non-parametric assumptions. So that's again beyond the scope of this class, but just kind of this isn't just any central limit theorem, it's a good one too. So this is nice. And actually the proof gives you more than what I wrote down. It actually tells you that kind of, okay, algorithmically, you can write tau hat AIPW as the average of these capital gamma hat i's. I'm going to call these things double robust scores. You're going to see them occur several times in this class. So you can think of tau hat AIPW as being an average of double robust scores. And these double robust scores, of course, are not IID. They're not independent from each other in general, because you plugged in these mu hats and e hats in there, and this kind of induces dependence across terms. But the thing is that actually, under the assumptions we made, that is under the assumption that e hat and mu hat w converge at 4-through rates, then these gamma hats are close enough to being independent that you can ignore this dependence, and you can build confidence intervals for tau as though tau hat AIPW were just an average of gamma hats, and these gamma hats were independent. So you can just do the usual thing. I'm spelling it out here, but this is really kind of, if you stare at it, this is just the usual estimate of variance for a sample mean. And this is just kind of the usual asymptotically normal construction for confidence intervals for a sample mean. So you can kind of just really do kind of very standard things for building confidence intervals for tau once you're working with this AIPW estimator. So that's really nice. That's essentially, it's hard to kind of ask for much more than that in terms of guarantees. I just wanted to kind of close out this discussion by highlighting a few details that I neglected to mention in the statement of the theorem, but are still important. The first is, I should put an asterisk on the claim that you can just kind of plug mu hats and e hats into the AIPW estimator and everything is fine as long as these are accurate. This is almost true, but to make this actually true, you need to use this algorithmic trick called cross-fitting. If you're familiar with cross-validation, it's a very similar idea. The simplest type of cross-fitting is you divide your data set in two. You fit kind of models on both half of the data. And then when making a prediction for the ith observation, if the ith observation is in data half A, use the model trained on data half B, and vice versa. If the ith observation is in data half B, ith the model trained on data half A. So essentially, you never want to be making predictions like mu hat 1 of xi at the ith training example using a model that actually got to see the ith example while being trained. So that's something that matters. You really should use this. Most standard packages that kind of do AIPW based on machine learning will do it for you. If you want to implement it by hand, you need to remember to use cross-fitting. But kind of, it's a little bit of effort, but it's really kind of algorithmically, it's no more work than cross-validation. And this kind of, the guarantee you get out of cross-fitting is that kind of idiosyncrasies of how machine learning methods use individual data points don't affect your guarantees. So this is the first detail. The second is, I did have one more assumption on the slide. So kind of for AIPW to give good estimates of the average treatment effect, you need unconfoundedness. You need the machine learning methods to be reasonably accurate. And the third thing you need is you need overlap. And overlap here means essentially that the propensity scores can't get too close to 0 or 1. And specifically, I'm going to assume that there's kind of positive constant eta such that kind of everyone has at least a probability eta of being treated, and at most a probability 1 minus eta of being treated. There are no people in the data set who conditionally on X are essentially deterministically sent to control or treatment. There are many reasons you'd want to have overlap. Conceptually, it might feel kind of funny to try to estimate treatment effects in a data set where some people are deterministically assigned to treatment and or control, and there's kind of no kind of genuine treatment variation. If you kind of feel worried about that, you're right to feel worried about that. Another kind of just more algorithmic argument for why you don't want propensity scores close to 0 or 1 is that in this kind of variance of AIPW, you're dividing by E of x and 1 minus E of x. And if you're dividing by E of x and E of x is close to 0, that's going to blow up. So essentially, even kind of given all the guarantees we have here, if you let propensity scores get close to 0 or 1, your variance is going to be very bad. And your treatment effects won't be accurate. So what should we do about this? In applications, I'd recommend you kind of think about overlap. It's generally not something that you'll need to worry about too much, for the kind of simple reason that kind of in any given application, you can check if you have overlap or not. It's not like unconfoundedness, which is kind of one of these identifying assumptions that you just need to kind of sit down for a long time and think about whether you believe in it or not, but you can't validate from data. Overlap, right? If you're running AIPW, you have estimates of the propensity score. So just every time you have propensity scores, make a histogram. If the histogram is kind of nicely between 0 and 1, far from the extremes, you're in good shape. If it's spiking near 0 and 1, you may have a problem. And so just to show this in the case of an example from a paper from Susan and co-authors, they were studying a setting where you have you want to study different auction mechanisms, and the question was, what's the effect of using an open, sealed auction versus an open ascending auction? And they have data from Idaho and California here. Here we say that an auction is treated if it's sealed, and the propensity score would be the probability, conditionally on covariates, that the auction would be sealed. So then kind of here in this data set, you can kind of do what I was suggesting, that is make histograms of the propensity scores in both Idaho and California and see how it looks. In Idaho, everything looks good. So this plot actually shows density plots, not histograms, and it also stratifies by treatment type. So I believe this one is a density plot for the treated units versus for the controls. But overall, you see you're in pretty good shape. Most of the kind of propensity scores are far away from 0 and 1. You're in pretty good shape. You might probably that you have kind of quite a bit of propensity scores that are kind of stacked near 0 here. Maybe you should be estimating an average treatment effect on the treated. Anyways, there are solutions to get around these problems. But anyways, this is looking very good. On the other hand, same data set, but in California, all the controls essentially have a propensity score of 0, and all the treated units essentially just have a propensity score of 1, which suggests that kind of most of the data set, what was happened is kind of based on covariates. If you were a control, it was that you were going to deterministically be a control. If you're treated, then you were going to deterministically be a treated unit. And if your propensity score plot looks like this, then you have something to be concerned about, and you should do something about it. What can you do about it? There's a number of things. And this is kind of a fairly wide literature. I'm not going to go on it today, but you could kind of filter your data set into regions where kind of you have better overlap. Your propensity scores are less extreme. You could try changing the question. You could kind of, if you have a lot of propensity scores that are close to 0, but you don't have a problem near 1, you could estimate an average treatment effect on the treated. This is kind of another alternative to the average treatment effect, for which you can kind of do everything we've done in this lecture, but kind of in separate notation or kind of a slightly different functional form. So I'm not going to do that here. But essentially, you have a problem, but once you know you have a problem, you can often solve it. And this is something I'm happy to talk with if you encounter this kind of issue in your project. I just wanted to kind of really flag this as a thing to be paying attention to, because every couple of months, someone kind of sends me a bug report being like, I tried to run AIPW and nothing was working and everything blew up. And then I asked them, can you give me a histogram of your propensity score? And all their propensity scores are deterministically 0 and 1. And then I can helpfully tell them that they were dividing by 0. And that's why they were having problems. Anyways, that's overlap. So in recap, what have we done in this lecture? We wanted to estimate the average treatment effect. The average treatment effect is one of the kind of most standard targets in causal inference. We wanted to estimate an average treatment effect in an observational study. And this meant that kind of we had to control, in some sense, for variables x, pretreatment covariates. And we wanted to use machine learning to control for these x's to avoid making parametric assumptions. And at first glance, right, there are many popular ideas for estimating average treatment effects. You could do a regression adjustment, you could do inverse propensity weighting, and you might think, I know what to do. I'll take the regression adjustment formula, but just plug in machine learning, and everything's good, right? No, unfortunately not. Machine learning methods are pretty accurate, but not as accurate as parametric models, and not as accurate as parametric models in well-specified parametric designs. So then kind of that didn't quite work. You don't get confidence intervals out of it. And then you could look at IPW. You could again say, hey, I know what to do. I see an inverse propensity score. I'm going to estimate my propensity scores using a machine learning method, plug that in, and that's going to work, right? Again, it's like, not quite. It's going to be consistent, but we're not getting guarantees that are comparable to kind of good root and rate parametric type guarantees that we need for confidence intervals. So, okay, is the situation hopeless? No. The simplest, most naive things you might want to do don't work, but you can put machine learning to good use for causal inference. You just need to do so using the right strategy. And here, one good strategy is AIPW. It's a kind of carefully designed estimator that starts with the regression adjustment, then uses IPW to correct the regression adjustment, and in doing so cancels out the errors of kind of the regression adjustment and IPW to first order. You might think that I kind of just pulled this estimator out of a hat and then it's kind of strange, but maybe that's true, but I'll just reassure you that it's a big hat and there are many other things you can pull out of that hat. And there's a theory for how to do so. And kind of really AIPW is just kind of one first example of an estimator with this property. If you've heard terms like orthogonal moments or double robustness, these are kind of very general terms that apply to AIPW, but also apply to many other estimators. So that's the big picture. What's kind of the difference between linear regression and machine learning? Kind of one thing you could say is that linear regression, when given a well-specified linear model, it has very good behavior, parametric behavior. Its errors decay as 1 over square root n, and everything is wonderful. But in a general setting, if the linear model isn't right, then linear regression is inconsistent. You get the wrong answer, and that's bad. Machine learning, on the other hand, it's more flexible. In a linear specification, it's going to be okay. In a general setting, it's going to be okay. The reason you want to use machine learning is to kind of get decent estimates of the thing you want to predict under considerable generality. And that's good. Using machine learning opens the door to a bunch of flexibility. But the cost of doing so is that now you need to remember that actually machine learning methods, whenever you deploy them, they're going to have errors that are generally a little bit bigger than what you're used to when using kind of parametric methods and parametric models. And you need to use kind of post-processing strategies that are robust to moderate final sample errors. In the context of average treatment effect estimation, we saw that AIPW is one solution with this property, and kind of throughout this class, we're going to be seeing more of that. All right, that's all I had for now. I'm going to leave you with some references just here. Kind of the first three are closer to what I was talking about today. They kind of outline this agenda in much more breadth. And this kind of first and third, you can think of more as kind of giving you the agenda and kind of generalizations of where you kind of, what are problems where you can plug machine learning in and get good kind of parametric type guarantees and confidence intervals for the causal parameter you're interested in. And then kind of this paper fleshes out what I presented today, but kind of in the context of deep nets, and actually proves the guarantees for deep nets that you need to use to apply these results for. I'm also putting these two results here. Today I talked more about this kind of non-parametric setting. There's a parallel, very similar kind of discussion of what happens when you want to use, you're in a high dimensional setting and you want to use methods like the lasso to estimate average treatment effects there, instead of things like trees or forest or boosting, like you would in a non-parametric setting. Not going to say more about that here, but if you're interested in the high dimensional setting, then these two papers are a place to get started.